All right, today we are tackling a physics challenge that's got a real dose of adrenaline. We're going to use the power of calculus to not just track, but to actually predict a snowboarder's wild ride down a mountain. So let's just dive right in.
So here's our whole setup. We've got a snowboarder starting from a dead stop, and their trip down the hill is described by this equation you see for position x. Now our job is to figure out their exact position, their velocity, and their acceleration precisely at the 5-second mark. You can think of it like we're taking a high-speed, predictive snapshot of their journey.
Okay, before we even think about crunching a single number, we really need to get our heads around the core relationship here. This whole problem, it all hinges on the beautiful interconnected physics of position, velocity, and acceleration. You got to think of them like a family. Each one tells you something absolutely crucial about the others.
And the key that unlocks this whole thing, it's the derivative. Now please don't let that word scare you. A derivative is basically just a speedometer for any equation. So while the position equation tells you where you are, its derivative tells you your speed at that exact tiny instant. It's the tool that shows us the rate of change.
And this slide right here, this is our game plan. It's so simple and elegant. We start with the equation for the snowboarder's position. We use our derivative tool on that equation, and boom, we get their velocity. Then we just do it again. We use the derivative tool on the velocity equation, and that gives us their acceleration. It's a clean, logical, one-way street.
All right, enough theory. With that down, it is time for the main event. Let's actually calculate what is happening to our snowboarder at that 5-second mark.
Step 1. Position. Now this is the easy part, really, because the problem already gave us the equation for x, which is the snowboarder's displacement. This formula is our crystal ball. It can tell us their exact location on the slope at any given time t.
So what do? We just take our target time, 5 seconds, and plug it right into the equation wherever we see a t. This gives us 0.5 times 5 cubed plus 5 squared plus 2 times 5.
You run the numbers, and there it is, our first answer. At exactly 5 seconds into the ride, the snowboarder has traveled 87.5 feet down the hill. Awesome. One piece of the puzzle is officially solved.
Okay, now for step 2, velocity. How fast are they going? This is where we get to use our new tool. We take the derivative of that original position equation, and that gives us this brand new formula for v, for velocity. This tells us how fast the snowboarder is going at any moment.
And hey, you know the drill by now, right? We just pop 5 seconds into our new velocity equation. So that's 1.5 times 5 squared plus 2 times 5 plus another 2.
Which gives us a speed of 49.5 feet per second. Now hold on, because this is where it gets really interesting. What does that actually mean? Well, that's nearly 34 miles per hour. Our snowboarder isn't just kind of cruising along, they are absolutely flying down that hill.
And finally, we get to the last piece of the puzzle, acceleration. This tells us how quickly the snowboarder's speed is changing. And to find it, we just take the derivative one more time, this time of the velocity equation we just found. And look at that, it gives us this really clean, simple formula for acceleration, a.
You know what's next. We plug in 5 seconds one last time, which is just 3 times 5 plus 2. Super simple.
And there you have it, 17 feet per second squared. So what's that mean? It means at the 5-second mark, the snowboarder's speed is increasing by 17 feet per second every single second. They are picking up speed, and they're doing it fast.
So we did it, we have our 3 numbers, we've done all the math, but what do they really tell us when we look at them all together? Let's paint the full picture.
Here it is, our 5-second snapshot. In one single instant, the snowboarder is 87.5 feet down the slope, traveling at almost 34 miles per hour, and is still speeding up significantly. You see, this isn't just a list of numbers. It's a dynamic story of motion, a story that calculus lets us tell with perfect accuracy.
You know, that leads to a pretty powerful idea. When you look at it this way, you start to realize that calculus, it isn't just abstract math. It's a language. It's actually the language our universe uses to write the poetry of motion, whether that's a planet orbiting a star or, yeah, a snowboarder carving down a mountain.
So, why does any of this matter beyond a fun physics problem?
Well, because these exact same principles are the bedrock of so much of our modern technology. They power the GPS in your phone. They help engineers design safer cars. They plot the trajectories of rockets heading to Mars. They even create the super realistic physics in your favorite video games. It's everywhere.
So I'll leave you with one final thought to chew on. Our math showed us that the snowboarder's acceleration, which was a equals 3t plus 2, isn't a constant number. It actually increases over time. So thinking about the real world, what might that increasing acceleration tell you about the actual shape of the hill they're riding down? Something to think about. Thanks for joining me.